Welcome to chemistry class. We are in session 5 of the chapter gaseous state. In this session, let us understand the Graham's law of diffusion. So before understanding the law, let me first remind you about the definition of diffusion. Did you ever heard the term diffusion? Yes? What it is? Let me give you an example to get you to the definition of diffusion. Suppose one of your family member is spraying a perfume on his clothes and you are feeling that smell of that perfume even though you are at the other end of the room. Why it is so? Because the molecules of the perfume, they are traveling through the air and reaching you, isn't it? So what is happening here? Irrespective of the Earth's gravitational force, these gas molecules are moving randomly and occupying the entire available space, isn't it? That process is called as diffusion. For example, you can even see this animation to understand that. See, these gas molecules, they are trying to occupy the entire available space. They are not stationary, they are moving randomly and they occupy the entire available space, isn't it? So this property of spontaneous intermixing of gases to form a homogeneous mixture is called diffusion. So originally in this air is present. Now when the gas molecules are moving into that particular part, so they are mixed up with the air uniformly. And this property of spontaneous mixing of gases to form a homogeneous mixture, that is called as diffusion. And a slight modification of diffusion is there, which is effusion. And see what is happening here. It is the escaping of the gas under high pressure through a small aperture, that is called as the effusion. So here the gas molecules are coming into this particular vacant space through the small aperture. This is called as the effusion. So what is effusion? It is a process in which a gas is allowed to escape under pressure through a fine orifice or a small aperture made in the wall of the closed container. That is called as the effusion. So that is the basic difference between diffusion and effusion. So what is diffusion? It is a spontaneous intermixing of gases to form a homogeneous mixture. Irrespective of the Earth's gravitational force, these gas molecules move randomly and occupy the entire available space. And if this diffusion takes place through a small aperture under high pressure, that is called as effusion. Now let's understand the statement of Graham's law of diffusion. At constant pressure and temperature, the rate of diffusion or even effusion of a gas is inversely proportional to square root of its density. So rate of diffusion, I write it as R, that is inversely proportional to square root of its density, and that is at constant temperature and pressure. So if R1 and R2 are the rates of diffusion of two different gases, then R1 by R2 is equal to root over D2 by D1, where D1 and D2 are the densities of the two gases respectively. And this one we can write like this. Instead of density of the second gas, we can divide the density of this gas with the density of hydrogen. So square root of density of the second gas divided by density of hydrogen upon density of the first gas divided by the density of hydrogen. So doesn't matter, as we are dividing the density of both the gases with the density of hydrogen. Then in place of density of the gas upon density of hydrogen, we can write that is vapor density of gas 2 upon the vapor density of gas 1. And why we can write like this? Because vapor density is nothing but equal to the ratio of density of the gas and the density of hydrogen. So in place of density of gas upon density of hydrogen, we can write vapor density of gas 2. Similarly for the case of the gas 1 also. Suppose when we multiply the vapor density of both these gases with 2, what we will get? Now R1 by R2 is equal to 2 into vapor density of gas 2 upon 2 into vapor density of gas 1. Now instead of writing 2 into vapor density, I can simply write it as molecular weight of gas 2 divided by molecular weight of gas 1. Why it is like that? Because you had learned in basic concepts of chemistry that 2 into vapor density is nothing but equal to molecular weight, isn't it? So in place of 2 into vapor density, we can write molecular weight of the gas. So I can write all at one step like this. R1 by R2 is equal to root over D2 by D1, which is equal to root over VD2 by VD1, which is equal to root over M2 by M1. So for majority of the numericals, as they mention the names of the gases, definitely we can compare the rate of diffusion with their molecular masses. Means R1 by R2 is equal to root over M2 by M1. Because from the names of the gases, we can definitely get their molecular masses. So now let's understand what is the meaning of rate of diffusion. And rate of diffusion is nothing but the volume of the gas diffused in time t, means that is V upon T. So that is the reason why now I can write R1 upon R2 is equal to V1 upon T1 into T2 upon V2, which is equal to root over M2 upon M1, isn't it? Again, this will be useful for working out some numericals. Now let us take two cases here. First case, under similar conditions, if same volume of two different gases diffuse in different time intervals, then what happens? This R1 by R2 is equal to V upon T1 into T2 upon V, which is equal to root over M2 upon M1, isn't it? As same volume of the gas is diffusing in different time intervals. So R1 by R2 is equal to T2 by T1, which is equal to root over M2 by M1. That is R1 by R2 is equal to T2 by T1, which is equal to root over M2 by M1. Now let us take the second case. Now under similar conditions, if different volumes of two gases diffuses in the same time. So here two different gases of different volumes are diffusing in the same time. Then what happens here? R1 by R2 is equal to V1 by T into T by V2 is equal to root over M2 by M1. Means R1 by R2 is equal to V1 by V2 equal to root over M2 by M1. As here the two gases are diffusing in the same time, time will be cancelled out. That is R1 by R2 is equal to V1 by V2, which is equal to root over M2 upon M1. That is about this Graham's law of diffusion. And these are the various mathematical relations we come across in Graham's law of diffusion. Now let's see the effect of pressure on the rate of diffusion. We had already learned that rate of diffusion of a gas is inversely proportional to square root of its molecular mass. And we need to know one more point. Rate of diffusion is directly proportional to the pressure. Because when more pressure is applied, definitely more gas will be diffused. So combining both these relations, we get R proportional to P upon square root of molecular mass. So therefore, R1 upon R2 is equal to P1 upon P2 into square root of M2 upon M1. So that is how the pressure is affecting the rate of diffusion.